Hello everybody, it's our last video notes of Unit 4. Okay, we're going to be able to do all of this stuff, hopefully, after we listen to this. Okay, so keep listening, read this section and this section in your book. Hey, want video note bonus? Do that. Okay, so here we go. We're going to talk about acids. Acids we're going to treat them as ionic compounds, but special ionic compounds because they all have something in common. What they have in common is hydrogen. All acids have one thing in common when we talk about them, and that thing is hydrogen. So usually the acidic hydrogen, or the hydrogen that makes it acid, is placed in front of the chemical formula. So what is this thing? It's an acid. How do I know? Hello, hello, hello. Acid. Hello, acid. How do I know you're acid? Because you start with hydrogen. What kind of compound is this? Acid. How do I know? Hello. It starts with hello, hydrogen. Hello, hydrogen. You must be an acid, an acid, an acid. Okay. So first you got to recognize. And today's show is brought to you by the letter H because hydrogen is the letter that starts all of our acids. Okay. So there are some rules for naming acids. Here's what they are. First, recognize it's an acid. How? Hello, hello, hello. They all start with hydrogen. That's how you know it's an acid. Then, if every acid starts with H, then we can't name it hydrogen something. So we're going to have to look at what it finishes with. All right? All of these two finish with just a single element, and that single element is called the anion, and it's an ion that ends in IDE because it comes from the periodic table. So the ending, if the anion ends in IDE, then you have to put this prefix hydro in the name, and then you have to put this ending ic acid. Here's how it is. HCl is called hydrochloric acid because we know it's an acid, starts with H, so we got to call it an acid, and then we have to put the prefix hydro and the ending ic acid on there. Okay, this H2S. Okay, how do I know it's an acid? Hello, starts with H. So then the second part is called sulfide. So what do? You put the prefix hydro and the ending ic acid on sulfur. Okay, so hydrosulfuric acid, H2S, is hydrosulfuric acid. So please put these rules into your notes so you have them. Hey, look, it's an acid. Hello, how do I know it starts with H? So then we look at the second part. The second part of this you memorized is sulfite. Okay, so what you do is you change, you're going to call it an acid because it's an acid, and then you put the stem of the word in the us acid. Okay, us acid. So H2SO3, it's an acid, so you look at the second part, sulfite, ite turns into us acid. This is sulfurous acid. All right, what about this one? HNO2. Well, NO2 is nitrite, so I changed the ending to us acid, so this is nitrous acid. I know it's an acid, I write the word acid. Okay, there's three different kinds of acids. There's hydroic acids, there's us acids, and here's our third kind. I know it's an acid, starts with H. Then if the anion, the second part of the compound, ended in H, all right, then I just put ic acid, no prefix. Okay, no prefix. So PO4 negative 3 is phosphate, so I drop the 8 and I put ic acid, and it's phosphoric acid. Okay, ClO3 is the second part of this acid. I know that's chlorate, so I drop the 8 and I add ic acid. It's chloric acid. So there's three kinds of acids. There's hydroic acids, there's us acids, and there's ic acids. How do you know which is which? Well, it all depends on the anion that it's with. Okay, so let's practice. H2S. What is it? It's an acid. Hello, hello. It starts with H. Hello, it's an acid. So now I look at the second part, which is S. I know it's S negative 2. The name of that is sulfide. So I'd use hydro and then sulfuric acid. Okay, so I'd use hydroic acid for that one. Right. H2SO4. Hello, it's an acid. It comes from SO4 negative 2, which is sulfate. Sulfate, H turns into ic acid. Sulfuric acid. Okay, sulfuric acid. And then H, hello, it's an acid. comes from SO3 negative 2. That's that part. Okay, so I would call this sulfite. Ite turns into us. Sulfurous acid. Okay, so I made up a little song. It goes like this. Hello, I'm an acid. I start with hydrogen. And once you recognize them, we're ready to begin. Look at my second part and think of what it is. And remember this song to get it the right name. If you ate it, it was icky. And then you got the itis. I'd use hydro-ic. Yeah, I'd use hydro-ic. I'll sing it in class for you 100 times. All right. Hey, if you want to write the formula of an acid, we got to be able to do that too. How do you know it's an acid? Well, look at this. This says hydronitric acid. Hello, it's an acid, so that means it's got to start with H. H is in column 1, so we're going to make it be a +1 for these compounds. All right. I notice it says hydro and ic, and so I know it came from I'd. I'd use hydro-ic. So this must have come from nitride. All right, nitride. So then I go to the periodic table, I look up N, I see it's in group 5A, so they make a -3 charge. Now we have to cancel charge. This doesn't equal 0. That doesn't equal 0. That equals 0. So the chemical formula for hydronitric acid is H3N. Okay. Hey, look, this next compound, I got to write its formula. Hey, it's an acid. How do I know? It says acid right there. Okay. So then it's ic acid. Right, so I know I have to have an H, and H has a +1 because it's in group 1. I know it's ic acid. I ate it. It was icky. So 8 turns into ic. So this must have been nitrate. So then I write down nitrate. See, aren't you glad you memorized it? And then I have to make it equal 0. Heck yeah, it equals 0. HNO3 is nitric acid. All right, what about this one? Us acid. This is an acid. Hello. I'm going to start with H. All right. Us acid. I ate it. It was icky. And then I got ite us. So this comes from nitrite. So NO2 negative, because I memorized it. Hey, that equals 0. So this is nitrous acid. Okay, so you better be able to write the chemical names and the chemical formulas for acids. That's what we're doing there. Okay, now this is the only kind of substance we haven't talked about, and it's metals. Right? Metals. What holds metals together, or how are metals held together? Well, they have variable bond strength. Some metals are held together very strongly, some are not. They have variable melting and boiling points, although a lot of them are high, some of them low, can melt in your hand, and mercury is already a liquid. Okay, they are good conductors of heat and electricity in their solid form. Okay, and also in liquid form. But most of the time we're talking about metals, they're going to be solids, except for mercury. They are malleable. That means you can hammer them into shapes. They have high luster. They're ductile. You can make wires out of them. Okay, so here are properties of metals. We've talked about this before, but now we're going to talk about what the heck's holding them together. So the metallic bonding model is that metals bonded to other metals or to themselves do not form compounds. So this is iron. This is silver. Those aren't compounds. Those are elements. Okay. Bronze has 2 metals in it, but there's no chemical bond. It's just metallic bonding. Okay, so it's not a compound. Metallic bonding occurs through what we call non-directional, so not in one direction, sharing of electrons. Not in one direction. Okay, so another way to say that is called the sea of electrons. So here's aluminum, right? And if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, aluminum's supposed to have 13 electrons, but this aluminum only has 10. So this is really an aluminum cation with a +3 charge. Another one, another one, another one, another one. So what's holding all these aluminum cations together? Well, see these are aluminum's valence electrons. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There's lots of them because 3 outer electrons from this aluminum and 3 from that 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 aluminum. Those are the valence electrons that can be shared by all of them in all directions. Okay, so these valence electrons of the metals kind of come off of each metal so that each metal turns into a cation, and all of the valence electrons are used by all of them. Okay, that's what I mean by not in one direction, but in all directions. These electrons are kind of shared between all of them. Okay, so how does this explain metals' properties? Well, if all of these are gold atoms, and gold has all its electrons except its valence ones, then all of these ones out here are the valence electrons that are used by every one of those gold cations. Okay, so these are the sea of electrons. So they can move. They are mobile. They can move. Right? So because they can move, this shows that metals conduct electricity. Okay, these are metals. All of these are metals. Metals conduct electricity. Why? Because those outer sea of electrons can move through metals. Okay, so they conduct electricity. Mobile valence electrons. Okay, that's the sea of electrons. The sea, or all of them can use all of them, and you start on one side, you can push electrons through because the charge can be carried. Okay, you add heat to a metal. Okay, those outer valence electrons, that sea of electrons, can pass the heat from one atom to another. Okay, show conductivity of heat. So they're good conductors of electricity, metals. Good conductors of heat, metals. Okay, why are metals malleable? Well, if you have all of these metal nuclei with their core electrons, their cations, all right, and then you have this sea of electrons holding them all together. If you hit them with a hammer, all right, so here's my hammer, all right, you can make them bend, and then that sea of electrons still can hold them together. They don't shatter, they don't crack at first. I mean, you can make them crack, but they're malleable because that valence sea of electrons holds them together. Sea of electrons holds them together, so they're malleable. They can bend before they break. All right, so here's what we talked about in this unit. We talked about ionic bonding. That first lab we did, we saw that ionic compounds were brittle and they were solid. There was a repeating pattern of positive, negative, positive, negative, positive, negative, negative, positive. All right. All right. So if you hit this with a hammer, you put a positive next to a positive and it shatters. That's why they're brittle. They do not conduct as solid because these ions are stuck in place when they're solid. They might dissolve in water, many of them do, and when they are dissolved, then you have positives and negatives all over the place dissolved, so then electricity can flow because those charges can move. So when they're dissolved, they can conduct, okay, or when they're liquid, they can conduct. How are they formed? Their electrons get transferred from the cation to the anion. How is that different than what we just learned about? Metallic bonding. Metals are shiny, malleable solids, except mercury is a liquid. The atoms turn into cations with mobile outer electrons. Okay, they do conduct as solid because those mobile electrons can pass current through. They don't dissolve in water, although some metals do react with water. What's the deal with their electrons? Well, they get shared in all directions by all the metal cations. Okay, so those are the two kinds of bonding to explain the properties of two kinds of substances we're looking at. So now pulling it all together with all the bonding that we've been talking about. Okay, new kind, metallic bonding is two metals. It's the sea of electrons. They conduct as solid and liquid. They have variable melting points. Some are high, some are low, some are in between. They do not dissolve in water, and they have variable bond strength. Okay, a new one, ionic. Metal and a nonmetal. The valence electrons are transferred from the cation to the anion. They conduct as liquid or as aqueous, but not as solid. They have the highest very high melting points compared to most of them. Most of them are soluble, so they have high bond strength because they have high melting points. How is that different than last unit? You still have to know this, okay? Covalent was two nonmetals. They are held together by valence electrons being stuck between atoms. So hydrogen is sharing those two valence electrons, but they're stuck there. They can't move around. So they can never conduct electricity. Covalently bonded things are the only ones with low melting points, but some of them have high. If there's polar molecules, they should dissolve in water, okay, but some of them don't. And they have high bond strength, but they might have low intermolecular forces, so they could be gases at room temperature. Okay. All right, so here's some models for bonding. If you're looking at all of these, hopefully you're seeing ionic bonding. Solid crystals, ions stuck in place, ions stuck in place. Okay, so they don't conduct when they're solid. They're brittle when they're solid because you move a positive next to a positive if you hit it with a hammer. Oh, look at that hammer. All right, that's why they're brittle. Metallic bonding. You have all these metal cations, so they're shiny. So look at this would reflect light. Reflect light. All right, and then they're malleable because these can move and adjust. They conduct electricity because those valence electrons can flow through. So metallic bonding model is all the positive cations lined up, and the sea of valence electrons gets to be used by all of them. Covalent bonding. Oh, look, it's sugar, it's water, it's carbon dioxide. Covalent bonding, electrons are shared between two nonmetals. Okay, sulfur hexafluoride. So you can have liquids, solids, gases. Okay, the electrons are stuck in between the atoms. They can't move, so they won't conduct electricity. But then if the molecule's polar, it could dissolve in this polar water. Sugar's polar, dissolves in water. 3 kinds of bonding. Got to know them all. All right, so what type of bond is made of 2 metals? That's metallic bonding. Conduct as solid. The only ones that conduct as solid are metallic. All right. Has a low melting point. The only ones with low melting points are covalent. Maybe some metals. Okay, electronegative difference of 2.2 is ionic. This is nonpolar covalent. Covalent. All right. Transfer electrons, ionic. Share electrons evenly, covalent. And there's 2 kinds of covalent. Nonpolar covalent is that one. Has the highest boiling point, probably ionic. Okay. Is soluble in water and has a high electronegativity difference, is ionic. Soluble in water has a low electronegativity difference, is probably covalent with polar molecules. Okay. That's a tough one, but we'll keep practicing. Has mobile electrons shared by all cations, is metallic. Okay. So now we can look at all the stuff around us and try to classify what's holding it together. So to review, all right, and we'll play little music while we review. Okay. Hello, I'm an acid. I start with hydrogen. You got rules to name those. The metallic bonding model explains properties of metals. Okay, with the sea of electrons. Memorize your ions, peeps. Okay, your single charged ions from the periodic table or your polyatomic. Metals have valence electrons C. That describes all the properties. Covalent bonds share valence electrons evenly or unevenly, but they're sharing. Okay. Ionic bonds transfer electrons from the cation to the anion. How can you predict what kind of bond is present? All right. Look at the properties. Look at the electronegativity difference. Look at the type of atoms. Okay. Make sure you have evidence to back up your bonding claims. All right. All right. So make sure you read this. Do those numbers for video bonus. And now, can we do it? Check it out. You know these 3 kinds of bonding. You can tell what happens to electrons. All right. Hello, I'm an acid. And then describe properties. All right. So that's it. See ya.